Hello, I am Kons from IBM Research. I will be presenting extending RNN-T-based speech recognition systems with emotions and language classification. The voiceovers for the rest of this video were synthesized using the next generation of the IBM text-to-speech.
Recurrent Neural Network Transducer, known as RNN-T, is currently a leading speech recognition architecture. Its main focus is speech transcription, but it can be trained on additional tasks. This can help us to extract additional information from the speech and to get a richer transcript. In this paper we examine two tasks: emotion classification and language identification. For emotion classification, we trained RNN-T models to produce emotion tags in addition to the text transcript. We tested this on two datasets and found that we can get classification accuracy close to other state-of-the-art emotion classification models. For language identification, we developed a new classifier architecture based on the encoder network of an RNN-T model. Our tests shows that this model can achieve state-of-the-art results. We start with emotion classification. A common approach to this problem is to train a specialized classifier that uses embedding models on the input speech or text and then apply a classifier to identify the emotion. Our goal is to integrate this ability into the ASR model so it will output rich transcript with both text and emotions. Most speech emotion datasets are small, which make training good speech model hard, but, in our case, we can use pre-trained ASR models that were already trained on a large amount of speech data. Another benefit of this approach is that the classifier can learn from both acoustic features and, also, the transcribed text. We train the RNN-T model to produce emotion labels by adding emotion tags to the text transcript at the end of each utterance. Each tag is represented by a unique symbol that is added to the output character set of the model. In our test, we used 4 emotion tags: neutral, happy, angry and sad for both datasets. Phrases with other emotions labels were discarded from the dataset. We tested this on 2 datasets, the IE-mocap and the MELD datasets. On the top graph you can see the classification accuracy for the 2 datasets. The first part shows the results for our suggested model, where the whole RNN-T model was fine-tuned to produce the emotion tags. For the second part, we repeated the experiment, but this time, the acoustic encoder part of the network was frozen during the training, so the classifier can only extract emotion information from the textual and phonetic input. We can see that the gap from the previous experiment is not very large, so it seems that most of the information comes from there. For comparison, we also present results for state-of-the-art, emotion-only classifiers based on Wojtek and Hubert, as presented in a previous paper. As can be seen, both are more accurate from our RNN-T classifier. Since our model does both emotion classification and speech transcription, we had to verify that the transcription accuracy does not degrade after our modifications. The second graph shows the word error rates for the baseline unmodified model and for the models after our training. As can be seen, in most cases the accuracy improves, except for the model using the frozen encoder in the IE-mocap dataset. The second part of our work deals with language identification. This is usually required when transcribing speech in an unknown language. One approach is to apply a language classifier on the speech and then, if our system can handle this language, use the corresponding STT. This two-step solution can cause large latency because the speech is processed by 2 different modules. Another solution is to use a multilingual STT, but these are much harder to train and required transcribed training data in all languages. In addition, many multilingual systems require the language to be identified during transcription. The solution that we suggest works like other state-of-the-art language classifier that process the speech with an embedding model and then apply a classifier on its output. However, instead of using a general self-supervised model such as Wojtek or Hubert, we are using the encoder network of a single language, RNN-T model, as shown in the drawing. The classifier network apply a bidirectional LSTM on top of the encoder output and then a weighted average pooling. During training we keep the encoder frozen and train only the classifier network so that the STT functionality will not be impacted. Although the encoder was trained only on one language, we can still use it for training a classifier on other languages too. During speech transcription we first apply the encoder network and then the language classifier. If we detect that the input is in the correct language, then we can continue the STT decoding with the encoder features that we have already extracted. We tested this classifier with the NIST LRE7 dataset. The dataset contains train and test data for 14 languages. We trained a classifier using an encoder module from a pre-trained US English RNN-T model. The results for different utterance duration from 1 to 30 seconds are shown in the graph. The results of our model are compared to state-of-the-art Hubert-based classifier presented in a previous paper. We can see that our new model's accuracy is close to the Hubert classifier for the short utterances and better for the longer ones. In addition, we trained models where we allowed fine-tuning of the encoder too. This provides additional accuracy improvements but breaks the STT functionality. In summary, we showed that the RNN-T model can be extended to extract additional information from the speech. On the first part, we showed that we can use it for emotion classification, but additional work is needed to improve the accuracy. On the second part, we presented state-of-the-art results for language identification by adding a classifier on top of the RNN-T encoder. This allows to perform language classification before the STT transcription with only minimal overhead. If you are interested, you may find additional details in the paper. Thank you.